Hi, hello everyone. I'm just taking your time slot just before the lunch. Sorry about that. I'll try to be as crisp as possible about the topic. The earlier presentations, the former presentations on different interesting topics have given certain dots that I can surely connect in my presentation. So this is going to be more about the kind of simulation engineering or the kind of virtualization that we can apply with a proper understanding of the present modernization trends and the requirements, especially the safety critical requirements that come up to address the railway needs basically. So that's the kind of agenda we are going with. So, well, we know that when we look at a railway project or a railway mission, it's composed of a lot of different systems, subsystems, components, a lot of complexity basically, and this complexity is basically interconnected to different components of a particular railway machine in several different ways. So this interconnectivity and taking upon a broad level, higher level overview picture is where we are focusing upon with this particular topic, model-based systems engineering. So systems engineering is basically about staying at a broader overview level, collecting the stakeholder requirements, and as thus formulating actions and implementations, and we specialize in rendering simulation solutions to a lot of functionalities that are associated with the railway technology. When you adopt system engineering, it's about linking a lot of functional components, basically systems, subsystems, etc. And this basically is going to give a full functionality overview in a virtual environment, and that's what we exactly need. So this takes away the disadvantage of several different teams that are going to work as a holistic project team for a particular railway project in silos, preventing them to work in silos. The systems engineering thought process and approach brings them to be integrated into one converging point, basically. So when they converge at one point, they would have better data analysis and data exchange, and that way they'd have a better idea of the traceability of various stages of the project. So we take a top-down approach, basically in this case, which would be demonstrated with the famous V model as well. So you have the idea of a system of systems, and then you can have a system. The system would contain a lot of subsystems and then a lot of components. Okay, this is an abstract level representation, but the subsequent slides would touch upon the specifics as well, getting to be more subjective in the level of detail about all these concepts. So this is a V model. So the advantage of this one is that it starts at a very higher overview, a stakeholder who wants certain things to be done. So in this case, the stakeholder could be as high as somebody like a Ministry of Railway Operations, in fact. And then it could come to a very high level technical and managerial techno-economic kind of team, which is functional with the broad level of Indian Railways. And then it could go to a specialized engineering team to carry upon the task. So since we very much start with the stakeholder requirements, build a system architecture model, and relate properly documented requirements onto physics-based simulation solutions. This is the navigation that I'm going to show you in the subsequent slides. Yeah, so we already have arrived at a more subjective detailed slide wherein you see several different types of tools that we have got in our particular physics-based solution portfolio projected in the form of a V model. So immediately when you collect the stakeholder requirements, we have tools which are really meant for mission engineering. For example, you would see over there STK, and I have a slide where I can show you that the GNSS, the Global Navigation Satellite System, is able to control the speed of railways in Europe. So European Space Agency is directly working with the European railways already in a very advanced state regarding this. So the way these satellites are moving, they are adjusting themselves to the orientation in their orbit, and then at the same time controlling the speed or signaling for the speed of the railways or the train that's going on the railway tracks. So this whole mission environment can be simulated by a software called STK. It uses flight dynamics, orbital mechanics, these sort of physics-based principles, basically. So that's like at a very higher level. And then when you look at this particular mission itself, you have got satellites which are monitoring the train. The train itself is a system, and the satellite is another system. So when you really look a overview about that, it's a system of systems overview that we are looking at. Now then comes the requirements about the systems that are participating in this system of systems definition. And after that, you could divide it into subsystems, of course, which could comprise about different types of control units within a railway machine. And then when you subdivide these control units, you would also see PCBs or power converters, batteries. These are the component level details, and there are tools which can simulate basically those details in a very physics-based sense as well. So that's about the whole holistic way in which you capture several details in a very methodical, organized, connected sense. With a V model, with the system engineering approach, we avoid teams and physics-based interactions staying in silos. We bring them to integration and coherence. Well, this is what I wanted to show. I think now it gets more subjective and a little bit in detail. So what you are seeing on the screen is basically two sedan cars which are traversing on the road, accompanied by a neighbor who is adjoined to them like a truck, basically. So this is a vehicle-to-vehicle communication system wherein you can see with our tool HFSS, there is a high-frequency electromagnetic simulation, and the cloud that you see over there is basically the radiation pattern from the antennas. The two antennas of the two autonomous vehicles, which are in this case two sedan cars on the road, are communicating with each other, and you can see antenna to antenna coupling signal traced out. So all this is virtually done. So basically you're going to trace out how indeed these cars are in simplistic sense going to keep a distance apart, not going to collide ever with each other by communicating. The cars are just talking to each other. So now each car has got, say, its own systems, which are control units, and then you divide them into subsystems, which could be other smaller type of control units, and then coming to components, it could be basically a battery, as I said, or a PCB, basically. That's how the V model basically proceeds. Now, say sedan 1 is system 1, sedan 2 is system 2 for you, system 1 plus system 2, that's a system of systems idea. So the stakeholder requirements, the end goal is that these two should not collide, they have to be a certain distance apart. That's the simple example. It could get complicated and bigger than that, definitely. So that's the system of systems idea. The stakeholders ideation or the conception basically begins from such an overview, and it cascades down to the component level as low as how do you control the thermal management or the cooling of a PCB that is working on either of these cars, basically. So the simulation that you see here is a high frequency electromagnetic simulation. In parts of US and Europe, we are already seeing this to be implemented as a vehicle-to-vehicle communication technology in the railways as well. So we are really talking futuristic technologies here, yeah. And another futuristic technology where I said global navigation satellite system is controlling the trains, basically. So in this case as well, you can see all these satellites combined together, and the train over there is a system of systems idea. And as I said, this STK as an orbital mechanics software can give you the details of how in real time the satellites are progressing and doing their proper job to send signals and maintain proper communication with the train. You can imagine the train in this case to be a ground station, basically. That's how it is. Well, as I already mentioned it, the European Space Agency and the European Railway Network have partnered together very well, and they have been working, hitting the railroad very well on the R&D side, basically. So as it comes, of course, to ISRO as well, I think there's a partnership between ISRO and the information network systems that are there with our Indian railways as well, basically. But we definitely hope that that partnership between ISRO and Indian railways can also mature and see greater heights like this one, the project that we are talking from European Space Agency as well. So we do have simulations which can capture the operations like these as well. Yeah. So basically the point is, when these electrified trains are running, and if they have to run very, very safely, then they have to, via sensors, take in and interpret a lot of information, process a lot of that basically. So that calls upon to take absolute care about the embedded software that is driving these cranes. And these embedded softwares can be safer, mission critically safer. When you assure them to be functionally safe, you attribute them to be functionally safe with certain standards that they are complying with, a lot of reliability and efficiency standards. And going further, the kind of compliance that you have to have with especially EN 50128 or 50126, 50126X basically, these type of standards is also very much important in this particular case. So you're going to see the compliance basically of the railway embedded softwares onto these particular standards. And for that, we do have a model-based approach using the particular tool called CAD, wherein you can just bring in the functionality of such embedded software by basically taking care of building it using a model-based environment. You do have already predefined blocks which you can drag and drop and build the software, and once you just do that, the code is already ready. You would get a C code or a ADA code, which would be the embedded software, which is now going to be compliant automatically to this particular standard EN 5012X. So these foggy environment are so, for a simple example's sake, if I have to state so, if it is not able to process a particular red signal in a particular way and the train just flashes off basically. So this signal is not just one that goes to a particular sensor. There is a cascading. A sensor is again in the back end attached to a group of sensors. It is a stack of sensors that have to critically process any signal that comes. A traffic signal is just a very small example. A speed controller sensor could function in a misalignment as well because of a faulty software, and the reason could be that it was in the first place not complying perfectly with a laid down standard like that. So yeah, SCAD, that's where it allows you to basically take upon those things, and what you are seeing is its extended capability with another software called Méridien over there, which will again offer the same easy to go model based environment and keeps you to be able to follow all the standards in the case of functional safety as well. So you can do safety requirements perfectly, FMEA, HAZOP, HERA, or the fault-free analysis, DFMEA. So all these, instead of doing them with Excel sheets or point tools, there are companies which have reported a consistent productivity increase and the time intensity decrease by 57%, as high as that, when they have moved away from Excel sheet based workflow to put up with that. Instead of that, they would come to a model based environment like Méridien. Even companies like Airbus, Boeing, I mean, in the aviation, you can imagine how more critical the safety requirements are, how more mission critical they are. But those companies are as well able to cope by using these type of model based environments. So definitely railways, Indian Railways are a very good candidate to adopt these type of technologies, undoubtedly. Yeah. So you just are seeing right now how architecture is built by using a SCAD suite, and that way you generate ADA code or a C code which is automatically compliant with the necessary standards over there. Yeah, so another one is model center. Basically, when you have a mission, an entire mission is to be integrated and analyzed as if it's a one-piece story, not in bits and pieces, not in silos, right? Then you need to have a proper integrator. That's where the role of ANSYS Model Center really comes in, and it completes the definition of model-based system engineering in a virtual sense, basically.
Excuse me, sir, one more minute left.
Yeah, sure.
Yes.
I'll try to wind up. So this is about putting up a block diagram. In this block diagram, you already put up the requirements from a stakeholder, and the stakeholders can relate them and kind of relate them basically to analysis parameters. These are parameters which go into the analysis softwares directly. So for example, outer diameter for a brake pad over there. So brake pad has to take this much of stress is something given as a requirement on the left side, and that will be related to a particular variable called OD, for example, on the right side. It is nothing but the outer diameter, for instance. That's one example of that. Yeah. So you just see how a system architecture model, which is very abstract in the sense, just containing the requirements from a stakeholder who may not be sometimes even technically oriented. He may come as an economic buyer basically, right? So those are getting related to a particular software which will do further analysis Just a message that we are working very closely with Deutsche Bahn as well, basically in Germany. So they are thriving very well with digitalization initiatives, encouraging a lot of startups. ISRO is doing this very well, and so we probably are hoping to have the same sort of synergy from Indian Railways as well, wherein they encourage very openly these startups. This is their web page, basically. When you go to Deutsche Bahn, you see exactly the whole list of a lot of startups. This is the opening page where you can just see a lot of startups coming and working. We are working with a lot of startups there already. So if there are any startups here, we have very good solutions to offer here as well from the perspective of working together with Indian Railways as well. So maybe in the networking sessions, we can look it up, in fact. So there is one startup which was just figuring out its own place. Level analysis, you can see braking system, a sort of crash worthiness when two trains are colliding. So these are just component level simulations. We just did not want to limit with these kind of routine simulation framework, because these are anyway covered in the component level of the V model that I just described in the beginning when I started my presentation. But the most important thing is to have a broader overview of a systems engineering perspective. So just taking the reference of NCRTC, where they have launched greatly this semi-high-speed train, right? So you see China's growth over there from, I think, 1960s to the 21st century. Just a simple component like pantograph has been changing its way of the material it is being made with. I mean, in 1960, they had a speed of 100 kmph. They used a pure metal pantograph slide. And right now they are operating 400 kmph, and they have migrated to a novel pantograph slide made up of composite material with a very special manufacturing technique. They have leveraged simulations, of course, in that. So you see on the slide basically what kind of characteristics a pantograph material has to possess in order to sustain the thriving promotion or the thriving progress in high-speed rails, basically. So on the right side, you do have ANSA Grant MII. So this is a very special tool which can make things easier in terms of material selection. For example, on the left side, you have ablation resistance, electrical conductivity requirement, wear resistance. If you just put those requirements in a proper way, behavior in a virtual physics-based sense, you can impose operational conditions and see its behavior, basically. So these are the different tools that you can use. You have optics, electromagnetics, structural, computational fluid dynamics, everything in one go, and all of them integrated in a systems engineering approach. So with that, I end my systems engineering demonstration. Thank you very much for attending.